Okay, we're going to continue talking about zeros of polynomials, but let me tell you this. A polynomial can have many types of zeros. Like if I had a polynomial, let's say I factored it into this form, notice that x equals 0 is a real number, is a solution, -5. Fraction like 4/3 could be a solution. Minus square root of 3 and plus square root of 3 could be a solution. And even 2 minus 5i and 2 plus 5i could actually be solutions. So let me do this other problem and kind of use it as a segue into this particular section. Now, I kind of shortened you on this problem, so let's take a look at this one. We can solve this equation if it's difficult to solve right now, but if someone tells me that x equals 3 is a 0, then I can reduce it using synthetic division. So actually that should say 3. So 3, divide 3 into this. These are the coefficients. So, do synthetic division, bring the 2 down. 3 times 2 is 6, and then add 6 to -3 and I get 3. Then 3 times 3 is 9, add 9 to -11 and I get -2, and then 3 times -2 is -6, and 6 plus -6 is 0. So basically I reduce this to a product of, since 3 was a solution, so the product would be x minus 3 for one factor, and then this polynomial here, 2x squared plus 3x minus 2, is another factor. Well, once I get this broken down to once I get this into a quadratic, well then I can either factor this to get the roots, or I can use the quadratic formula. Fortunately, this factors into 2x minus 1x plus 2. So now I know that this actually factors into 3 binomials, and I can set each binomial equal to 0 and solve it to get the x values of 3, 1/2, and -2. And so that's kind of what we're going to do in this next section to a certain extent. Okay, so if we want to find zeros of this, well, we're not going to have somebody telling us that, hey, -3 is a 0 or 2 is a 0. We're going to actually have to figure that out. Well, the rational zero theorem helps me figure out what the possible roots to a polynomial are, and basically what you're going to look for is the leading coefficient here, a sub n, and then the constant term, a sub 0. So the set of all possible integer coefficients would be p over q, where p is a factor of the constant terms a sub 0 and q is a factor of the leading term a sub n. So in this example, we know the constant term a sub 0 is 4, and we know the leading coefficient a sub n is -1. So p, let's list all possible factors of a sub 0, 4. Well, plus or minus 1, plus or minus 2, plus or minus 4, all are factors of 4. Now list all possible factors of a sub n, -1. What are all the possible factors of -1? Well, just plus or minus 1. And we're talking integer factors. Okay. Now let's list all the reduced possible factors of p over q. Well, we could take plus or minus 1 over plus or minus 1. Well, that's just going to give me plus or minus 1. Then I could take plus or minus 2 over plus or minus 1, so that's going to give me plus or minus 2. And then plus or minus 4 over plus or minus 1 is going to be plus or minus 4. So basically we have 6 possible zeros. And so those are the possible zeros. Now I'm not going to solve it just yet. Let me show you another example. Here a sub n is actually 15, and a sub 0 is -2. Okay, so to get p, I need to come up with all the possible factors of -2, which is plus or minus 1 and plus or minus 2. And to get q, I have to have all the possible factors of 15, plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So now, if I look at all the possibilities, I've got quite a few of them. If I take plus or minus 1 over each of these numbers, I get plus or minus 1 over 1 over 3 over 5 over 15. And then if I do plus or minus 2 over each one, I get plus or minus 2 over 1 over 3 over 5 over 15. Now I don't think I have any duplications here, but obviously you don't have to write them twice. So I've got these 4 sets of factors. Actually it's 8 counting the plus or minus, and then these 4. So we have actually 16 scenarios. These 8 values can be plus or minus, so that gives us 16 scenarios. Okay, let's stick with this one and let's see if we can maybe reduce this down somehow. Now let's start with the easy ones like plus or minus 1, plus or minus 2. Okay, so let's start with 1. If I try to use 1, then notice I bring the 15 down, multiply, I get 15, add it here, get 29, multiply 1 times 29, put it here, add it, I get 26, 1 times 26, add it. Okay, that didn't work because I didn't get a remainder of 0. So let's try negative 1. Okay, so let's try negative 1 here as a root. So bring the 15 down, negative 1 times 15 is negative 15. 14 plus negative 15 is negative 1, then multiply, negative 1 times negative 1 is 1, and then add it to negative 3 and I get negative 2, and then negative 1 times negative 2 is 2, put it here, add it to negative 2, and I get 0. Okay, so now I've got it reduced down to where I have a second degree factor. So I know x equals negative 1, so x, that means x plus 1 must be a factor. So if x plus 1 is a factor, then I can say this has got a factor into x plus 1 times 15x squared minus x minus 2, and these coefficients come from over here. Now then from there it should be pretty easy. You just factor that trinomial, and now you get 3 factors and set each of those factors equal to 0 to get your answers, negative 1, negative 1/3, and 2/5. And if you check, those were all listed as the possible roots. Okay, now I'm going to do this one next, and if you check all the p's and q's, you'll find that the possible p's over q's are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So I'm going to start with 1, and notice that I didn't get a remainder of 0, so we ditch that. So now let's go to negative 1, and when I do negative 1, notice I do get a remainder of 0. I'll let you go through the synthetic division yourself. So now this is going to be x squared plus x minus 6 for the other factor. So since negative 1 was what I tried, then that means, and I got a remainder of 0, then x plus 1 must be a factor. And so it must factor into x plus 1 times x squared plus x minus 6. And then it turns out that x squared plus x minus 6 factors into x plus 3x minus 2. And so then by setting each of these 3 factors equal to 0, we know the solution is these 3 numbers. Okay, let's do one more. So this one, p is plus or minus 1 and plus or minus 3, and q is just plus or minus 1. So the only solutions are plus or minus 1 and plus or minus 3. Now, I won't walk through each one of these, but let me show you I tried 1, and 1 didn't work because I didn't get a remainder of 0. I tried negative 1, that didn't work because I didn't get a remainder of 0. So I'm going to move up to, I might try, I've only got 3 and minus 3 left. So let's try 3. Well, I tried 3, and guess what? I didn't get a remainder of 0. So the only thing left for me to try is negative 3. So now when I tried negative 3, brought the 1 down, negative 3 times 1 is negative 3, add it to 7, get 4, multiply, negative 3 times 4 is negative 12, add it to 11, get negative 1, multiply, I get 3, and then add that to negative 3, I get 0. So now I have a quadratic here, x squared plus 4x minus 1. So this factors into x plus 3 times x squared minus 4x plus 1. Well, this trinomial will not factor over the integer values or the numbers I need to, so what I had to do was get the quadratic formula to solve this. So using a equal 1, b equal 4, and c equal negative 1, I just used the quadratic formula, and I found that I get these irrational numbers, negative 4 plus or minus 2 square root of 3 over 2, which can be simplified to negative 2 plus or minus square root of 3. So this first factor tells me that x equals negative 3, and then the other two factors are these two irrational factors, minus 2 minus square root of 3 and minus 2 plus square root of 3. So basically, using this theorem, we can get a set of possible factors, integer factors anyway. We can get a set of possible factors. Well, I said integer. It's actually, the factors are of the form of an integer over an integer, because you can have a fraction. And by exhausting that list, we eventually should come up with a factor that helps us reduce the problem to where I can get a factor that's of a lower degree. Okay, now this one's not a lot of fun because you got a lot of factors for 24, but here's the list of possible roots here. So I'm just going to kind of speed through this. I tried 1, I didn't get a remainder of 0. I tried negative 1, didn't get a remainder of 0. I tried 2, and I got a remainder of 0. So that means this factors into x minus 2, and then the coefficients are 1, 2, negative 12 to give me this trinomial. So now let's try this trinomial. Now we know plus or minus 1 will not work because it didn't work in the first place, and it rules out plus or minus 24 because now we've got negative 12. So we still got the same list, except we can't use this and we can't use these. So I tried 2 again, and when I did 2 again, I got a remainder of 0. And so now that reduces that from a 3rd degree to a 2 degree. So now, since 2 worked again, the factor was actually x minus 2 quantity squared, because minus 2, or 2 has a multiplicity of 2, and then I got this into a quadratic. So now to solve that, I just need to get the rest of the answers, I just need to solve that quadratic equation. And when you solve this quadratic equation this time, using the quadratic formula, you're actually going to get, and you know how to do the quadratic formula, but you're actually going to get 2 non-real numbers. So you get 2 real roots, 2 and negative 2. I got using synthetic division, and I'm sorry, I didn't get negative 2, my bad. I got 2, but I got it twice using synthetic division. And then the other roots were the 2 non-real roots, minus 2 plus or minus 2i square root of 2. Okay, you can do this one for practice. The roots are given below it. Okay, if a polynomial has degree n and you count all roots separately, even multiple roots, then the polynomial is going to have n roots. So what we're saying here, if you go back to this original problem, the degree was 4, and if you count the 2 twice, because it occurred twice, that's 2 roots, and then you've got these 2 non-real roots, so that gives you 4 roots. So it's the same as the degree, same number of roots as the degree. So how many roots did this have? Well, the degree is 3, so if you count any roots of multiplicity, then n equals 3. And if you go back and check, you'll see that n equals 3. Okay, now one thing that I want to mention here, if a plus bi is a non-real root, then so is a minus bi. So anytime a plus bi is a root, then a minus bi must be a root. So if you have 3 plus 2i as a root, you're also going to have 3 minus 2i as a root. And I'll finish these last couple of theorems on the next video.